R6 radicals and rational exponents. Before we dive into the new stuff, let's do a little warm-up reviewing what we learned in R5. So we have these rational expressions that are being subtracted. So hopefully when you look at that, you know that the first thing we need to do is to factor. So we've got to get those denominators factored. This first one has a common GCF. So we can take an x out and we're left with x minus 6. And the next one has a leading coefficient of 1, which is great because that means we don't have to split the middle. So we can just figure out what multiplies to get negative 24 and what adds to get negative 2, which is negative 6 and a positive 4. All right, so now we need to figure out what our LCD is going to be. We have to include all the factors in it. So it looks like we need an x, we need an x minus 6. This x minus 6 is already represented. So then we need an x plus 4. All right, and then we're going to multiply by what we're missing. So we need to multiply this first fraction on the left by x plus 4. This whole thing. And then this whole fraction on the right by x. All right, so if I distribute the 5x through to the x plus 4, I end up with 5x squared plus 20x. It was a subtraction problem, so minus 4x squared. All of that is over the LCD. Remember, we want to keep the LCD factored, so don't multiply the LCD together. All right, so then we want to combine our like terms. 5x squared minus 4x squared is x squared plus 20x. After we simplify our numerator, we want to see if there's anything that we can factor. And in this case, there is. Both of our terms have an x. So we can take that out. We have x plus 20 over x times x minus 6, x plus 4. And the reason we want to factor that numerator is because sometimes that means we can divide things out with the denominator. And in this case, we definitely can. We have an x on top and an x on the bottom. So if we divide those, they equal 1. So now our numerator is just x plus 20. And our denominator is x minus 6 times x plus 4. Since we got rid of that x, you don't have to have the x plus 20 in parentheses. You can, but it's not necessary if it's the only binomial that's up there. All right, let's take a look at what we're doing today. We're going to be dealing with radicals. So we'll start off with a simple radical here, square root of 16. Hopefully most of us know that when you take the square root of 16, you get a positive 4. Okay. Now what happens when we do the same kind of thing, but we throw in some variables? Let's take a look at this next one. Square root of 25, x to the 4th. Well, what you're going to want to do is think of these as two separate problems. So we're going to think of it as square root of 25 is one thing, square root of x to the 4th is something else. So think of them independently. So what's the square root of 25? Well, it's 5. Okay, so we're done with that. Now square root of x to the 4th. You may or may not remember that a square root is really an exponent of 1/2. So that symbol right there means you're taking something to the 1/2 power. So if we use our exponent rules, if we have x to the 4th to the 1/2, we would multiply these together. And 4 times 1/2 is x squared. So the square root of x to the 4th is x squared. So our final answer, 5x squared. So anytime you see a square root, it's always to the 1/2 power. All right, let's try another one. Here we have the square root of 80 times x to the 5th. Now again, we're going to want to separate these. So we're going to look at the square root of 80 independently from x to the 5th. But square root of 80 isn't a perfect square. So we've got to go back and find a perfect square that goes into the square root of 80. So you might have to make a perfect squares list. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, so on and so forth. 8 squared is 64. We need one of those numbers to divide evenly into 80. And we want to pick the biggest one because there's actually more than one that divides evenly. We want the biggest one that divides evenly into 80. 60. So I start at the biggest side. 64 doesn't, 49 doesn't, 36 doesn't, 25 doesn't, 16 does. 16 divides evenly into 80 5 times. So I put 16 on the left. The perfect square always goes on the left side, and the number of times it goes in on the right. So we can take the square root of 16 and get 4, and then just drop down the square root of 5. All right, so that's the part for the number, the 80, simplifying. But now we need to look at the x to the 5th. Now, if you remember before, we said that a square root was to the 1/2 power. So we multiplied the 4 times the 1/2 and we got it to be 2. It works really nicely when our exponent is even, but in this case, our exponent is odd. So what we want to do is break it down just like we did over here so that it's an even exponent, x to the 4th, times whatever's left over, x to the 1st. So x to the 4th times x to the 1st, they still add up to be 5, so we just broke it apart just like we did with the 80, breaking it apart to 16 and 5. So we have our even amount, because that's divisible by 2, this 1/2, and then we have our leftovers. So we're going to take the square root of x to the 4th, and then we have our square root of x. Well, we already talked about square root of x to the 4th. Take the 4 divided by 2, or 4 times 1/2. It's the same thing either way. So we get x squared times the square root of x. All right, so the last thing we need to do is put those answers together. The stuff that's on the outside, the 4 and the x squared, are on the outside together. And then the stuff on the inside stays on the inside together. All right, let's try taking a look at radicals with addition. So the only way that you can add radicals is if the radicand, so the radicand is this number underneath the radical, if these are the same. If the radicand is the same, then you can add the outside numbers. But of course, in this example, these radicands are not the same. So we would not be able to add this if we didn't simplify it first. So that's going to be our goal. We're going to simplify. So we need a perfect square that goes into 12. So again, looking at our list from before, we need one of these numbers that divides evenly into 12. That would be 4, and it goes in there 3 times. Do the same thing with the 27. We need one of these numbers that divides evenly into 27. That is 9, and it goes in there 3 times. So then we can simplify. This square root of 4 is a 2, and we drop the 3 down. The 3 is being multiplied. Same thing with the next group. We drop the 4 down. It is being multiplied by the square root of 9, which is 3. And we just keep the square root of 3. 3 times 2 is in fact 6. 4 times 3 is 12. So you'll notice now with our addition problem that the radicands are the same. They're both 3s. So this number is the same as this number, and that's called a radicand. Once they're the same, then we can add those outside numbers. So 6 plus 12 gives us 18, and you just keep the radical with that radicand, 18 radical 3, or 18 square root of 3. number 5, we have 4 divided by the square root of 48. You may have heard before that we don't like square roots or any radicals in the denominator. So we have to figure out a way to get it out of the denominator. So this is called rationalizing. And there's more than one way to go about this. 48 has perfect squares in it, so you could simplify it first, kind of like we did on 3 and 4. Or you could get rid of the square root first and then simplify later. It really doesn't matter either way. Let's take it with getting rid of the square root first. To get rid of the square root, you multiply top and bottom by the square root of 48. Notice if you multiply the top and bottom, when you have the same thing in numerator and denominator, it equals 1. So we're really just multiplying by 1. And multiplying by 1 doesn't change anything in a problem. So that's why it's okay to do that. All right, so our numerator is now 4 radical 48. But our denominator, when you multiply these together, remember we said before 48, the square root is to the 1/2 power times 48 to the 1/2 power. When bases are the same, you add the exponents together. So we would keep the 48 and add these. 1/2 plus 1/2 is 1. So 48 to the first, or just 48. So when you multiply 2 radicals together that are the same, it eliminates that square root sign. That only works with square roots. We'll talk later about cube roots. So when you multiply 2 square roots together, it eliminates that square root, as long as that radicand is the same. All right, so now let's look at the numerator. We have that square root of 48, which can be simplified. It has a perfect square that goes into it. The perfect square that goes into 48 is 16, and it goes in there 3 times. So the square root of 16 is 4, which we then have to multiply times this 4 that's already on the outside. So we get 16 radical 3 over 48. The 16 came from taking the square root of 16, which is 4, times the 4 that was already there. So 4 times 4 gives us this 16. All right, but we're still not done. There's still more simplifying we can do, because 16 and 48 have numbers in common. 16 divides into both of those. So 16 divided by 16 is 1. 48 divided by 16 is 3. So we end up with radical 3 over 3 as our final answer. All right, last one for this section, or this part of this section. We have square root of 3 over 4 plus square root of 5. When we have a radical in the denominator and it's being added or subtracted to something else, in order to get rid of it, we have to multiply times the conjugate. And the conjugate, what that means is you have to take the opposite of whatever the radical is. So we do 4 minus the square root of 5. Notice that we did not change the sign of the 4. The 4 is still positive. We just changed the sign of the radical. So we're going to multiply the top and the bottom. Since it's a binomial, you have to put it in parentheses so that you can distribute or FOIL. So in our numerator, we're going to take this square root of 3 and multiply it times both of those. When you have a number that's not in a radical times a number that is, you can't simplify those. So that just ends up being 4 radical 3. But when you take a radical times a radical, you can multiply those. So 3 times 5 gives us the square root of 15. All right, so same rules on the bottom. Go ahead and try to FOIL that. See if you can multiply all those things correctly. We have 4 times 4, which is 16. 4 times negative 5. And, sorry, negative square root of 5. Notice that we can't multiply those together. So it's square root of 5 times a positive 4. And square root of 5 times square root of 5. Square root of 5 times a negative square root of 5. Remember we talked earlier when the radicands are the same, you can multiply them together and it eliminates the radical sign, so just minus 5. And then we simplify anything that we can. So you'll notice that we have a negative 4 radical 5 and a positive 4 radical 5. So those two would add together to equal 0. And then we have 16 minus 5. So 16 minus 5, and our denominator would be 11. And then up in our numerator, 4 radical 3. 3 doesn't have any perfect squares that could go into it, so we can't simplify that. And then we check the 15. 15 also does not have any perfect squares, so it just stays as square root of 15. There's nothing else we can do to simplify, so that is our final answer. So lots of different things going on there with square roots, radicals, simplifying.